Hi everyone and welcome. In this video, we're going to take a look at solving a few trigonometric equations like these four, and then also figuring out what is the maximum and minimum value of this expression. So we have a lot of fun and interesting problems to get through today. And what you're going to learn is that there's a fundamental underlying principle that is going to help you solve these types of equations and these other problems. And so let's begin by first covering what that principle is, and then we'll solve each one of these problems. So what we need to learn is how to solve equations of the form a sine x plus b cosine x equals c, where a, b, and c are just some constants. And so it turns out that it's always possible to write a sine x plus b cosine x as sine of the sum of two angles. And you might be wondering, why did I pick sine? Could I also pick cosine of the sum of two angles? And yeah, you could also write cosine of x plus a different phase shift, right? Because sine and cosine at the end of the day are just the same function, shifted copies of each other. So yeah, if you can express this as sine, then you can also express it as cosine, just possibly with a different phase shift factor. Now, the thing that might be troubling you a little bit is, why is this k value here? Why can't we just write it simply as sine of x plus phi? Why is this k here? And the k is important because it's possible for the left-hand side to be more than 1. Right? It is possible for this quantity to have a sum bigger than 1 or less than 1. But the right-hand side, if you just had sine, we know that sine of anything is always between 1 and -1, right? The range of this function is between -1 and 1. So for that reason, you won't actually have an identity. It's going to be an equation that's sometimes true and sometimes not. So for that reason, we need to have this extra parameter k, this sort of amplitude, this vertical stretch factor, to make it actually always true. And so that's why the k value is there. That's why it's important. Okay, so now let's take a look at how to actually find my k value and my angle phi so that this equation is always true. And like I mentioned, you can work with sine or cosine. It doesn't really matter. For now, let's just work with sine. Let's come up with the k and angle values for sine. And so what we're going to do is actually expand this using the compound angle formula for sine. So we can say that a sine x plus b cosine x is k sine x plus phi for some positive constant k and some angle between 0 and 2 pi. So there's actually going to be infinitely many values for the angle, and you can actually take k to be negative as well. But we can just insist that k is positive and the angle is the principal angle between 0 and 2 pi. Okay, so to that end, what we'll do is use the compound angle formula and write this as sine of the first angle, cosine of the second angle, plus, same sign, cosine of the first angle, sine of the second angle. And then we'll distribute the k through to get this. And now the trick is going to be to match coefficients. Okay, so now if we match the coefficient of the sine x term, you can see we also have sine x term here. Then what that implies is that this k cosine phi should be a. And so that's my first equation. K cosine phi should be a. Similarly, we have cosine x, we have cosine x. So the coefficient here, k sine phi, that should be exactly b. And so that gives me my second equation. And so here we have a system of two trigonometric equations. And we have two equations, two unknowns. We should be able to solve for k and phi. Remember, a and b are just some constants. We're going to know what those are. We just need to figure out what k and phi are. And so here's one way to do it. One observation is that if I do a squared plus b squared, then that would be basically this thing squared plus this thing squared. And then if you apply the exponent properties, you get k squared cosine squared plus k squared sine squared. You can factor out k squared as common, and you're left with cosine squared plus sine squared. And that's the famous Pythagorean identity, is just equal to 1. And so what we see is a squared plus b squared is equal to k squared. And so now you can square root both sides, and we see that k is equal to plus minus the square root of a squared plus b squared. But since we want k to be positive, we'll just take the positive root. And there you go. So it turns out that when you're solving these kinds of equations, to find the k value, it's simply a squared plus b squared square root. That's how you get your k value. Now let's talk about how do we get our angle. So to get our angle, I'm going to go back to these two equations, and I'm going to solve for cosine phi and sine phi just by dividing by k on both sides, right? And what we get are these two new equations. So cosine phi equals a over k, and sine of phi equals b over k. And so there we go. We need phi to be an angle that satisfies both this and this. Okay, so that's important. We're going to do some examples just to make sure you understand that. But the point is, you cannot just take cosine inverse of one of these or sine inverse of one of these and get your angle. Phi has to be an angle that satisfies both at the same time. So if both are positive, well, then in that case, you're looking for phi that lives in the first quadrant. If cosine is positive and sine is negative, well, that will happen in the fourth quadrant. So phi is going to be a fourth quadrant angle. Similarly, if both are negative, well, then in that case, phi is going to be a third quadrant angle. And if cosine is negative, sine is positive, then you're looking for phi, which lives in the second quadrant. So usually you want to find the reference angle, and then based on the signs, figure out what the actual phi is. So we'll take a look at some examples and make sure that's clear. But just before we jump into the examples, let's just summarize the final conclusion. It turns out that a sin x plus b cosine x can be expressed as your k value, which is just a squared plus b squared square root times sine of x plus phi. And how do you find this phi? This phi needs to satisfy both of these conditions. Okay, so very, very nice. You're going to do this similar derivation in terms of cosine if you wanted to. It's going to be very, very similar. Just before we jump into the examples, I wanted to share another interesting fact about this expression, a sin x plus b cosine x. For those that are familiar with a little bit of vectors and dot product, it turns out that this is actually a dot product of the vector ab and the vector sin x cosine x. Now, the geometric dot product is defined as u dot v is the magnitude of u times the magnitude of v times the cosine of the angle between them. So the magnitude of this vector is the square root of a squared plus b squared. The magnitude of this vector, well, this is a vector that lives on the unit circle. Its magnitude is just going to be 1. And you can see that just by doing Pythagorean's theorem, sine squared plus cosine squared square root. The inside is just 1, square root of 1 is just 1, and we get cosine theta. And so what you see here is that this sort of represents a dot product. And this is our k value, which actually represents the length or the magnitude of this vector. And then if you were to write it as like, k cosine of x plus d, then this is sort of like the angle between the two vectors, what you see here. This is your k value. So very, very interesting. Okay, so now let's finally get started with the examples. The first equation we would like to solve is sin x plus cosine x equals the square root of 3 over 2. So we could redo the entire process and try to figure out how to make this equal to k sine of x plus phi. But let's just use the work, the results that we found, instead of having to redo that derivation. So the k value can be just found by doing a squared plus b squared square root. In this case, a and b are both 1. So we get square root of 1 squared plus 1 squared, which is square root of 2. That's the k value. And how do we find the angle? Well, remember, the angle is supposed to satisfy cosine of phi is equal to a over k, and sine of phi is equal to b over k. Well, in this case, the a values are both 1, and the k value we just figured out, square root 2, square root 2. And yeah, we're looking for the angle phi in which sine and cosine are both positive. Well, if sine and cosine are both positive, then that implies that phi lives in the first quadrant. So generally what you want to do is find the reference angle by using one of these ratios. Take the sine inverse or cosine inverse of the positive angle to find your reference angle, and then write the phi in terms of the reference angle. But in this case, phi lives in the first, it's the first quadrant angle, so it is the reference angle, right? Pi over 4. Very simple. But don't worry, in other examples, we'll see how this is not just going to be the reference angle. It might be pi minus or pi plus. We'll take a look at that. But yeah, right now, phi is just equal to your reference angle, pi over 4 radians. Okay, so now what we can do is take the left-hand side of this equation and rewrite it as k sine of x plus phi, where the k value is square root 2 and the phi is pi over 4. And all of this needs to equal the square root 3/2. Okay, to solve this trigonometric equation, we'll first write this as square root 3 over square root 2, then divide both sides by square root 2, which will make this a 2 down here. And now we're trying to figure out when does sine of theta equal square root 3/2, right? When is sine positive? Sine is positive in two quadrants, quadrant number 1 and quadrant number 2. And so what we can do is just find the reference angle for sine theta equals square root 3/2. It's a special triangle angle. It's going to be 60 degrees or pi/3 radians. And so one solution is pi/3. The other solution is going to be pi minus pi/3. Pi minus the reference angle. And so we just said, we're not looking for theta, we're looking for this thing. This thing must equal either your reference angle, or this thing must equal pi minus your reference angle, as we just discussed. And so now you can just plug in pi/3 in these places, and then subtract pi/4, and you get the general family of solutions. So one family of solutions is pi/12 plus 2 pi k, and another family of solutions is 5 pi/12 plus 2 pi k. Right? Why do we have this plus 2 pi k? Because the period of this function is 2 pi k. So if you have one solution, you can just wrap back around and get another solution, right? And so on and so forth. So since there is no interval specified or domain restriction, we have to specify the most general solution, and this is it. If there was a restriction, you can just pick k equals 0, k equals 1, k equals 2, and generate the solutions on that particular interval. But that's it. That's the end of this problem. Let's take a look at the next equation. We're trying to solve minus sine x plus square root 3 cosine x equals 1 on the interval from 0 to 3 pi. So the first thing we're going to do is figure out the k value. And so that's going to be the square root of a squared plus b squared. What's our a and b? Our a is -1, our b is square root 3. We plug them in here, and we get 3 plus 1, which is 4, square root that, you get 2. Okay, good. We determined k. Now, the angle needs to satisfy these two trigonometric equations, as we saw before. We plug in a value, we plug in b value, division by 2 on both sides. Okay, so now we're looking for when is cosine negative and when is sine positive. Well, that happens in the second quadrant. Here, sine is positive, but cosine is negative. So what we're going to do is we're going to use one of these ratios, doesn't matter which one. In this case, I used cosine inverse, of positive 1/2 to find my reference angle. Once I have my reference angle, I can use that to write the actual phi that we care about. So in this case, phi is going to be pi minus the reference angle. And so that's what we've written over here. It's 2 pi/3. Now that we have our k value and angle, we can go ahead and rewrite this as k times the sine of x plus phi. And this all equals 1. You divide both sides by 2 to isolate for the trigonometric ratio. And we have a very similar equation again. We have basically sine of theta equals 1/2. So that corresponds to solutions. Theta equals pi/6 and theta equals pi minus pi/6, which is just 5 pi/6. But we don't want theta, we want the solutions for x. So for that reason, we actually have x plus 2 pi/3 equals our reference angle, pi/6, that corresponds to this solution, plus 2 pi k. And similarly, we have the argument equals pi minus the reference angle, that corresponds to this solution, plus 2 pi k. And now what you can do is just sub this in here and subtract 2 pi/3 to combine it here to get this angle. Similarly, you can sub this in here, do pi minus pi/6, which is 5 pi/6. Combine the 2 pi/3 in here by subtracting it into this, and you get this angle. And so this is the family of all possible solutions to this equation. But remember, we're looking for solutions on 0 to 3 pi. So for that reason, we have to track the parameter that gives us those values in that interval. Well, this one is not in that interval. So I need to add a multiple of 2 pi. If I do that once, I get 3 pi over 2. That is in the interval. Now, if I add another 2 pi, then I'll end up leaving my interval. So this is the only solution here. Now, for this one, this is one solution that lives in 0 to 3 pi. But so is if you add 2 pi. If you add 2 pi, you get another solution in our interval. And so we actually have 3 solutions for this equation. Okay, so now let's take a look at the last question in this video. I highly encourage you to actually try this one on your own. This one is really going to make sure you understand what we've done. It's going to be a little bit of a different twist. So let's read this one. This one is saying, find a sequence of transformations which map the graph of the basic cosine function onto the graph of this 2 sine x minus 2 cosine x function. So in other words, what they're saying is write 2 sine x minus 2 cosine x as cosine of x plus phi times k. Okay, so this time we're not trying to write it as sine, because if it was, then you can just use the formulas we derived before. This time we have to write it as cosine. And so let's re-derive sort of like the new formulas for cosine. In fact, you'll see the k value is the same, and it's going to be very similar derivation and similar results for the angle as well. So to that end, let's go ahead and use the compound angle formulas for cosine to say that this is cosine of the first angle, cosine of the second angle, opposite sign, the minus, sine of the first angle, sine of the second angle. Distribute the k, and we get this. Now we're going to match coefficients just like we did before. If you take a look here, we have a cosine x term, we have a cosine x term. So what that means is that this thing should be the -2. That gives me our first equation. Similarly, we have sine x, and we have in front of sine x this -k sine phi term. So that should match with the 2 here. That gives me my second equation. So I have 2 equations, 2 unknowns. I should be able to hopefully solve for k and phi. So we're going to use the same approach. We're going to take -2 squared plus 2 squared, which basically means squaring these guys and summing them up. So now you use the exponent properties to distribute. You get k squared plus cosine squared plus k squared times sine squared. Factor the k out, and you're left with cosine squared plus sine squared. That's just 1. And so therefore, k must be the square root of -2 squared plus 2 squared. And we'll just take the positive root for the same reason as we discussed before. And so we get square root 8, which can be written as 2 square root 2. Great. Now that we have the k value, we can go back and plug it here and plug it here and get our constraints for the angle. So it turns out the angle phi should satisfy -2 over 2 square root 2, and sine of phi should satisfy 2 over divided by minus k, so -2 square root 2. Just like that. Now, let's go ahead and find our reference angle. To find a reference angle, use any of the ratios. Just make sure that you take a positive ratio when you plug it into the inverse function to indeed get your reference angle that lies in the first quadrant. Now, cosine and sine are both negative. When are sine and cosine both negative? Well, that happens in third quadrant. So we're looking for the third quadrant angle. And to write that in terms of the reference angle, we can just say it's pi plus the reference angle. Pi plus the reference angle. And so, therefore, the angle that we're looking for is pi plus the reference angle, 5 pi over 4. Awesome. So what we have here is that the graph y equals 2 sine x minus 2 cosine x can be written as sort of like a scaled up version of a basic cosine curve. That vertical stretch factor is going to be 2 square root 2. And then there's also a phase shift. That phase shift is 5 pi over 4 units to the left. And so there we go. It turns out this combination of sine and cosine is really just a scaled up version of a simple cosine curve, possibly with a phase shift. And now let's quickly take a look at the follow-up question that follows very nicely from part A. They're saying find the maximum and minimum value of this expression. So from part A, we know that this inside part is equivalent to 2 square root 2 cosine of this thing. And now why is that helpful? It's helpful because we know that cosine of anything is between -1 and 1. So that means this entire thing should be between 2 square root 2 and negative 2 square root 2, right? So if we know cosine is between negative 1 and 1, we multiply through in the inequality by this k value, and we see that this expression is between negative square root 2 and square root 2. And then I'll just go ahead and replace this with what the actual question is looking for. So it looks more like this. And then we're going to square this side. But whenever you square something, it's always going to be non-negative. It's always going to be non-negative. So this becomes greater than or equal to 0. And this thing squared. But that just equal to 4 times 2 is 8. And lastly, we have to just add 2 to all sides of the inequality. And we see that this expression is at least 2 and at most 10. And there we go. That's how you figure out the minimum and maximum value of this thing. And so now I just want to mention something about how to generalize this. If you ever see a sine x plus b cosine x, and they're asking for like a minimum or maximum value, well then you know that we learned in this video that you can write this as k like sine of x plus phi, or k cosine of x plus a different constant d. And these are always between negative 1 and 1. So that means that this will always be between negative k and k. And that's how you can figure out the max and min value of this thing. And then you might have to square or like add on the inequality and figure out the answer that you're looking for. But that's a general technique. Very nice. Okay, and I want to end this video with a very quick example to show that not all of these equations have solutions. So for instance, if you take a look at this simple equation, sine x plus cosine x equals 2, then we can calculate the k value as the square root of 1 squared plus 1 squared, because those are my a and b, and I get square root 2. So that means we can rewrite this as the k value times sine of x plus phi. And we don't actually need to find phi, because sine is always less than or equal to 1, right? Sine is always between negative 1 and 1. And so when I scale that, its amplitude is going to grow to square root 2. So this thing is always going to be between negative square root 2 and positive square root 2. But square root 2 is strictly less than 2. So yeah, this graph is never going to touch the horizontal line y equals 2. As a result, this equation has no solutions. And so there we go. That brings us to the end of this video, in which we solved some pretty fun, or at least I found them fun and interesting, trigonometric equations. And we saw an application of how to find like minimum and maximum values of stuff involving a sine x plus b cosine x equals c. This equation was really the key to solving these problems. Figuring out the principles on how to solve this general equation helped us solve these specific examples. So very, very nice. Hopefully you learned something new. Thanks for watching. If you enjoyed this video or found it helpful, I would really appreciate it if you could like the video and subscribe for more content. And if you have any questions or thoughts, feel free to leave a comment down below. I would love to hear from you.